everybody, welcome to lecture 2 over section 1.5, I believe. What lecture 2, what 1.5 is all about is just introducing this idea of the limit. Now, the limit is written something like this. That's a mess. What it reads as is the limit as x approaches a of f of x is equal to L. What the hell does that all mean? Right? Like that's the question we're all asking ourselves right now. What in all that is right in this world just happened up there? Well, what's happening, what this thing is saying is that if you were to let x get really close to a, we would say arbitrarily close in math. Like the proper way mathematicians would say is as x gets arbitrarily close to a. Your function, f of x, gets arbitrarily close to L. Now, we're going to see in 1.7, it's actually proven the opposite direction, that we assume something about what's happening in y, and let that guide us to what's happening in x, but you don't need to worry about that for right now. For right now, we just need to get through what does this even mean. Well, on an intuitive level, like I said, you can think of it as x gets arbitrarily close to a, your function will get arbitrarily close to L. So the value it spits out gets close to L. Now to see two examples of this in real life, we've got the limit as x approaches 1 of x squared minus 1. Then we have the limit as x approaches 2 of x squared minus 4x minus 4 divided by x minus 2. Now, right now, I'm just going to focus on x squared minus 1. We're going to come back to this example later. And for that matter, I'm going to pause the video in a few seconds after I go through this first example. And I want y'all to think about this bottom example. And see if you can maybe reason out where we're going to go with all of this. Okay, so the limit as x approaches 1 of x squared minus 1, it's just asking, what does x squared minus 1 get close to when x is close to 1? Well, okay. You can think of this a few different ways. We can start off thinking about it graphically. We've got x equal to 1 right here. So as we get close to x equal to 1 from the left, our function moves up like this, right? So we're moving from left to right. We're coming from down here, and we're moving up because we're going from somewhere off to the left towards x equal to 1. Move up like this. Okay. Well, if we were to take and look at what happens over on the y-axis, it would look something like this. We would just be moving up, right? Now, if we do it from the other direction, if we come at 1 from the left, so over here, well, then we're moving down the function, right? Like this. And if we were to think of this motion and what it would look like as a shadow on the y-axis, it would look like we're moving down. And notice what gets pinched would be y equal to 0. So let's come back over to this. X squared minus 1. Well, when x is equal to 1, we know it is equal to 0. So, yeah, obviously that sense, right? Seems like it does. So we can go about starting to answer some of these questions graphically. That said, there's another way we can go about this. We could go about this using a tabular approach. So drawing the table out, drawing out below. We could decide that 1 is somewhere in here. So let's have our left column be all of our x values and our right column be all of our y values. Let's say 1 is somewhere around here. We know our equation is equal to 0 and 1. We can pick now a couple other values above and below 1. So let's have this be, I don't know, 1.01. That's going to come out to be 1.01, that quantity squared, minus 1. I have no clue what that number is. But we could go one below. We could say, all right, let's start at 0.99. Same trick. 0.99 squared, minus 1. And we can fill out this table and look at, as we get close to 1, from above and from below, do these values squeeze in on 0? Well, 1 squared is 1. So 1.01 squared is going to be close to 1. So subtracting something close to 1, subtracting 1 from something close to 1, is still going to be close to 0, right? Same thing down here. And we're going to find that it doesn't matter what these values are above and below, as they get closer to 1, their answers, when you put them through the function, their answers are going to get closer and closer to 1. So this we could think of as delta x equal to negative 0.01, and this we can think of as delta x equal to 0.01. Huh. It looks like what we just talked about in the last lecture video, doesn't it? This delta x value showing up. And this is what I was talking about in that last lecture video when I said you're going to let delta x get smaller. Because as you go further out, the magnitude of delta x will get larger. But if you were to let it shrink in, you get really close to 1 here. And what corresponds is that the y values will get close to 0. So in this case, we would say that the limit as x approaches 1 is equal to 0. Now, unfortunately, this doesn't always work. The graphical method nor the tabular method always works. That sucks, I think. So we need to come up with some other tools to help us deal with limits. Those other tools are going to be algebraic tools. And they're going to let us solve this case in particular. We could do it tabularly. Yeah, we could do it tabularly. Because, check it out, as x approaches 2, well, you'd have a 0 if you were to just plug 2 into this, right? Because a 0 in the denominator, I mean to say. Because 2 minus 2 is 0. So you can't evaluate that outright. So when you put it into a table, that row would just be 2 and does not exist. You would have to look at what happens from above and from below. And you might be able to reason it out. But there are some functions that just get very chaotic looking, that swiggle up and down and do all sorts of crazy things. way too fast for a tabular approach to be meaningful. To show you an example of this, just draw a graph. We could imagine the graph of something like cosine of 1 over x. Right? This is not quite drawn the way I wanted it to be drawn. This. Right? So as you move close to x equal to 0, it just squiggles up and down. It just oscillates up and down as fast as you can possibly ask it to. Granted, none of that's drawn on this graph. But graph it, check it out, see it for yourself. This is one example, though, of where that table is going to fail. Because as you let x get arbitrarily small, you're going to find you just oscillate. You jump back and forth between values from -1 to 1. It doesn't matter what you use for your delta x. It doesn't matter how you shrink it down. It's just going to bounce crazily. So the table for something like cosine of 1 over x doesn't work. And graphically, there's a hole in this graph. This graph doesn't exist where x is equal to 2. And really, this graph just looks like a big black bar off to the left, right? Because it just oscillates so fast. So graphing and tables don't always work. And like I said, that's what this next video is going to be about. How to handle those cases. How to actually solve in a reasonable way the question of what is the limit as x approaches a of some function f of x. Stick around, there's more.